So today we're going to look at our last type of power. We've already seen lots of different types of power, and I'm going to recap them briefly at the beginning of this video. And then we're going to go on to have a look at irrational powers. So we've already seen powers from these number sets that I've written here. And just as a reminder from last year, this set of numbers is the natural numbers. And these are all of our counting numbers, including 0. So 0, 1, 2, 3, etc., etc. So all of the positive whole numbers. Then we have here our integers, z, which are all of the whole numbers, including the negative numbers. So negative 3, negative 2, negative 1 is included, as well as all of the positive ones that are also in the natural numbers. Then we have q, which are rational numbers. And these are all numbers that can be expressed as a fraction. So the decimal representation terminates or recurs. So if you have a number like 0.3 recurring, you know that that can be expressed as a fraction, or if the decimal stops, then that can be expressed as a fraction. And then we have all of our real numbers, which is any number that you can think of, which includes the irrational numbers. So just as a reminder, if we had our number sets represented as kind of circles, then we have the natural numbers are included within the integers, are included within the rational numbers, are included within the real numbers. And each of these sets, as we've discussed before, is infinitely large, but we have some infinitely large sets being bigger than other infinitely large sets. So there are infinitely many natural numbers, but you could argue there are almost twice as many integers, because it carries on in the negative direction as well. So we have almost twice times this infinity. So these are our number sets, and as you already know, we've seen powers in the natural numbers, in the integers, and in the rational numbers. Let's just have a quick recap of those. So, powers in the natural numbers. So we've already seen that if we have then for x in n, this means that a to the x is just a times by itself x times. So we've seen powers in the natural numbers many times, and hopefully you're comfortable working with those. Then in this unit, some of you were introduced to powers in the integers. Some of you were comfortable with them already. So, if we have x as a negative number, then this means that a to the x is 1 over a to the absolute value of x, or to the minus x. Let's say to the absolute value of x. So, for example, a to the negative 2 is 1 over a squared. So we've seen powers that are just natural numbers. We've seen powers that are integers. Of course, if x is positive, then it works the same as here. We've also seen powers in the rational numbers. So if we have x is written as a fraction, a over b, so x is an element of the rational numbers. Then if we have, let's say, let's call our base z this time to the a over b. This is the bth root of z to the power of a. So, for example, z to the power of 2/3, we have the cube root of z squared. So we've seen powers in those three sets. What we haven't looked at, though, are irrational powers. That's the set of numbers that are in this area of our diagram. So the real numbers that are not rational, they must be irrational. And of course that's what we're going to be looking at today. So, irrational powers. So let's first of all remind ourselves of some irrational numbers. I wonder if you can think of any off the top of your head. A couple that we met last year were pi, the square root of 2, and in fact the square root of any prime number is definitely irrational, so square root of 3, square root of 5. Now, what does it mean if we have a base and we raise it to an irrational power? Well, we don't have any rules as such, like we did with the other powers, of how we can find this. However it can be found, you'll notice if you type, let's say for example, 3 to the power of the square root of 2 into your calculator, you will come out with an answer. 3 to the power of root 2 should give you about 4.73-ish. And so you can evaluate this. However, we don't have these rules like we do with the other ones. So, how could we find this without a calculator? Well, the issue with irrational powers is we don't know the whole decimal expansion. You know, if we have the square root of 2, this decimal expansion is infinitely long. You've got 1.41421, and it carries on forever. So, we don't know this, or at least not all of it. So how could we possibly find something raised to this power when we don't really know what the whole number is? Well, what we can do is we can use something called approximation. And this is something that's used very, very often in maths. If you can't find something exactly, then what approximation says is find the nearest possible result to a good level of accuracy. Because for most purposes, we don't need this to 100 decimal places. A few decimal places would do, and then we have a slightly rounded answer that we know is correct to a certain number of decimal places. And actually, that's all your calculator does, because it doesn't use the whole infinite expansion of the square root of 2. It just uses quite a lot of the numbers, and then comes out with a good approximation that's correct to a good few decimal places. So how does approximation work in practice? Well, we start with, as we always do, what do we already know? Now, something I know about the square root of 2 is that I know it's about this, so I know it's greater than 1, but it's less than 2. This means that 3 to the power of the square root of 2 is going to be less than 3 squared, but greater than 3 to the power of 1. So, it's going to be somewhere between 3 and 9. So I've already found an approximation for this. However, I'm sure you'll agree that saying that a number is between 3 and 9 isn't particularly helpful for most practical purposes. So, I can go then to the next level of accuracy. I can go then to this second decimal place. So I know now that the square root of 2 is between 1.4 and 1.5, which means that it's between 3 to the power of 1.4 and 3 to the power of 1.5. And as we know, 1.4 can be converted into a fraction. So this one is 5/5 and 0.4 is 2/5. So we have 3 to the power of 7/5 and 3 to the power of 3 over 2. So it's between the 5th root of 3 to the 7 and the cube root, I keep getting these the other way around today, the square root of 3 cubed. Always the number on the top is the power that you're raising it to under the square root sign. Clearly I've forgotten this. So we can figure these out. Of course they're difficult to figure out on our own. Our calculator can of course do it. So if I do 3 to the power of 7 and I take the 5th root of that, I get 4.66 is less than 3 to the power of the square root of 2. And I know that 3 cubed is 27, so I just need to take the square root of 27 here. And 5.20. And already, just by taking the second decimal place here, we've come up with a much, much smaller interval than we had originally. We knew originally that it was between 3 and 9. Now we know it's between 4.66 and 5.2. And you can keep doing this until you get to an acceptable level of accuracy. And probably just one more level would do it. So we have 1.41. So we know that the square root of 2 is between 1.41 and 1.42, which means that 3 to the power of the square root of 2 is between 3 to the power of 1.42 and 3 to the power of 1.41, and 3 to the power of 1.41 is 4.71, or let's take it 4.707 to 3 decimal places, and 3 to the power of 1.42 is 4.759. So we've almost now got 3 to the power of the square root of 2 to 1 decimal place, and if we did this one more time we would definitely have 3 to the power of square root of 2 to 1 decimal place. In the next video I'm going to do exercise 98, and I'm going to do B because that involves pi rather than a root, which is maybe more interesting. I recommend, and this is on page 24, I recommend that you have a look at the exercise, try following this process through and seeing if you can come to the answer yourself, and of course you can check it on the calculator. If you're unsure, then watch the next video.